So as long as it unzips, you can ignore that file. That file will not play a large role in your explorations, which will probably make you glad because you don't want its name. Okay. So moving right along, ladies and gentlemen. What we're going to be doing today is using those models to explore the relationship between two things. On the one hand, what a model structure or structure of an underlying system on the one hand, and the data that system puts out. Okay, so in order to explore this, we are going to go here to talk about sort of nonlinearity, and we'll go into these particular models. So while I'm talking, you might want to load up these models. There should be a set of them. That's actually the first four that I'm going to be showing. Agent-based predator-prey, aggregate predator-prey, Lorenz, and SITS. Okay, so you may remember that when it comes to nonlinearity and models and systems that are nonlinear, one of the defining characteristics of a nonlinear system is one where the behavior depends on the state of the system. So it's not merely as susceptible, you have a certain chance per unit time of getting infected. It actually depends on the number of people that are infected already. So the behavior, the probability of making a transition depends on the current state of the system. In that case, the number of infectives, okay? By contrast, a linear system, the probability of something happening is independent of system state. So maybe we're dealing with a situation where, you know, we're examining people killed by lightning. There's just a fixed chance per year they'll be hit by lightning. It's independent of the number of people that have already been hit by lightning or the number of people in the population. It's just a certain probability per year that someone will be hit. For a nonlinear system, by contrast, this behavior depends on the state of the system in an important way. Okay, here, you know, we're talking about a situation where with nonlinear systems, we have behavior over that the system can engage in that is highly dependent on the current state of the system. Now, we depict the behavior of a system in many different ways. One way is over time, the value of a certain variable, but another way that I introduced some lectures ago, probably about halfway through the course, was this notion of a state space. So if I draw a state space, I'm going to draw it here in 2 dimensions because that's easier. And suppose we are considering an SIRS model, something like this. So we have these stocks here. And suppose I wanted to focus right now on S and I. What would a state space look like? Does anyone remember a state space depiction of this? Let's start it even easier to avoid confusion. Start it with S and I only. What would it look like? What would the axes?
The number of S on one axis.
Number of S and the number of I on the other axis. That's a state space description, right? And a given run of the model might start in a given place. Lots of susceptibles, few infectives, and might lead over time, say, to more infectives and fewer susceptibles, right? Until it reaches some equilibrium, for example, all right? Or perhaps it would, if we considered some additional stocks, it might actually loop around, but that would require some additional elements of state. Okay, now let's suppose we put an R in here. How many dimensions are there in this state space?
There's still 2.
Okay, there's still only 2, and why is that?
We are considering R dimensions.
Okay, excuse me, I'm gonna draw it like this, as I did originally. So how many dimensions would there be in the state space in this case? So we have SI and R comes back to S. Well, nominally, there's S, I, and R coming out of the board. Right? We could, at any one time, the system can be in a given state as a certain number of S, certain number of I, and a certain number of R out here, right? This is understandably a little bit hard to draw, so I'll be using other mechanisms to illustrate this. And over time, the system would undergo a trajectory in this three-dimensional space whereby it would evolve. Its S would change, its I would change, and its R would change. And so it would etch out a trajectory in so-called three space, in 3 dimensions, where it would move around within the state space. So this is a state space. You may recall that time within the state space is implicit. It's associated with the moving along a trajectory. So a state space, in short, provides an alternative way of depicting model evolution. It's an alternative to time plots. We could plot out as behavior over time, or we can plot its behavior within state space. And here, each independent element of model state, S, I, R, in that case, is associated with an axis. It's associated with one of these dimensions, one of these coordinates, one of these components of the coordinates. And a given run is illustrated with a trajectory. It follows a particular curve here. Time is implicit. It points along this trajectory. And importantly, for a nonlinear model, the model behavior can differ across the state space. Okay, this is somehow clipping at the bottom here, so I'm going to adjust this so that it's less likely to do so. Okay, so here we go. Okay, that didn't help much. Oh, man. Okay, great. So I guess I'll just have to make it smaller. Great. So we're going to pull out a couple of these models, and we're going to examine state spaces for them, okay? And summaries of the state space. The first one I'd like you to open up is going to be one for an aggregate predator-prey model, okay? So you have any logic there, and you have this file you downloaded from Moodle here, and I noticed Winchell came in here. So I'm just going to make sure that he also has a copy of this file. Maybe Young Chin, could you send Winchell a copy of that file?
Okay.
Yeah, thank you very much. Just so he can see this as well. Okay. So, ladies and gentlemen, we're going to go to AnyLogic here, and I'm going to open up here a copy of this model. So, this is going to be a model that's called. So it's called Predator, excuse me. Oh, okay. It's called Hare's Lynx Predator Prey. That's what it's called. Do you see that? Yeah? Okay, Hare's Lynx Predator Prey. No, I think somehow the name got screwed up. Okay, Hare's Lynx Predator Prey. You may have to go 2 levels in to open up this file. Okay? So this is actually one of AnyLogic's built-in models. It's a model which is a classic one, and it's a model that you may recognize from other sources. Okay, so here we have a number of hares and a number of lynx, and we're going to have lynx births and lynx deaths, hare deaths, and hare births. And lynx births are going to be determined here by a couple of things, lynx and lynx natality, okay? And lynx deaths are going to be determined by the number of lynx, but instead of being a fixed chance per unit time, it's going to depend on the number of hares in the area. So the hare density, not hares as in your head, but hares as in the small lapid, the small animal, okay? Similarly, hares are going to undergo births with a certain rate, fixed rate, but their deaths are determined by lynxes being around, okay? So if you go and run this model, predator-prey model, you will see some dynamics that you may recognize. What sort of dynamics would we expect out of a model like this? Anyone?
Oscillations.
Okay, good. So what do those oscillations represent?
As the amount of hairs grow, the links also grow.
Good.
As the links grow, they need more food.
Good.
So the amount of hairs decrease, which causes a decrease in the length.
That's right. And importantly, there's a delay here between the peak of the lynxes and the peak of the, between the peak of the hairs and the peak of the lynxes. You'll notice the lynxes here are multiplied by 100, so you could see them more easily. But basically, the number of lynxes, the hairs support the lynxes. They support the ability for lynxes to live. And yet, as the number of hairs rises, the number of lynx rise. And the number of hairs will max out even while the number of lynx continue to grow. The number of lynx end up overshooting the carrying capacity of the hairs. And even as the hairs decrease, for a short time, the lynxes still grow. There's this delay, and that leads the number of hairs to sort of really, really go down, and inevitably the number of lynxes go down as well. Now, this is a plot here over time showing the dynamics of that model. You'll notice down here below it, what I've shown is a depiction of three things. So one thing is the state space, and this is not dragging, so it's odd. I did this previously, but we're going to need to go to the model, and if we go to the model, we can go to the window area, and we should enable panning. I guess I was viewing on a larger monitor, so we're going to enable panning. Maybe you don't need it on yours. I need it on mine. That's associated with the simulation, and we'll come back to it, and we can see these lower plots. So this leftmost plot is a plot of hairs versus lynx over time. So that's simply the stocks, the hair and lynx stocks over time. And you'll notice that it forms a distinctive pattern. What is that pattern? What do you see in terms of the number of hairs and lynxes over time in state space? What do you see there? It's a cycle. It's a cycle. So as the number of lynx rise, this is hairs, number of hairs rise. Here we have a situation where the lynx also change, shown on the vertical axis. So with the largest number of hairs and the minimal number of hairs, we both get similar numbers of lynx here. The maximum number of lynx appear to exist when we have a moderate number of hairs here, okay? The minimum, yes, this is the maximum and this is the minimum. So this is depicting the state space of this model by showing hairs versus lynxes, okay? And if we go and we look at it here, we'll find that's how that graph is defined, okay? So hairs versus lynxes, and we have hairs on the x, and y we have lynx. But I've also shown two other things here that are going to be cause for discussion, and we're going to come back to them about what's going on here. But this is hairs versus hairs one time earlier, or lynx versus lynx one time earlier. We're going to come back to that theme in just a minute, okay? Next, I'd like you to go to another model that I'd like you to open. And this model will be a predator-prey model as well, but it will be an agent-based one. So it's called predator-prey agent-based modified for state space, okay? I'm glad it didn't say that name was too long, okay? So you can go open that model up. And here, we are going to see a depiction of the same basic model, same basic idea, but in an agent-based way. So here we have lynx. Lynx's job in life is to hunt, and if they're successful, they will eat. If they are unlucky, they will not eat, and after a certain amount of time or after starvation conditions, they can die. Okay? Eating brings them out of this state and back into it, which means they're not subject to this timeout. If they reach a timeout while staying in the state without eating, they die. Hare's job in life here is even simpler. Their job is to be alive and to have babies. Okay? It's very, very, very simple life cycle. Okay, so let's go run this model. This model I've also instrumented, though it wasn't in the original depiction, to show hairs versus lengths. And you'll find that over here. Unfortunately, I think in your versions of AnyLogic, you're constrained in the number of agents that can be created, so you can only run it for a shorter period of time. But I'm going to actually run it out here full tilt in a different version of AnyLogic that allows us to kind of depict it. And here, what we see is the state space, but we see the effects of what? Why do we see this kind of entangled mess here? It's stochastics, ladies and gentlemen. So you see there's cycles here, but it's not the neat cycles we see in the aggregate model. Instead, it's a kind of entropic element that seems to have a roughly circular form, but has a lot of entangled components. Okay, ladies and gentlemen, what I'd like to do now is to open up a third model. Okay, this is called the Lorenz Attractor. Now, this model is of considerable intellectual interest for several reasons. One of the reasons is because it was perhaps the first example, certainly one of the first, of what is known as a chaotic model, as a chaotic depiction of a chaotic system. By a chaotic system, I mean a system where if you start the system at 2 points that can be very, very close together, they can end up at very different ultimate places in the model. So, in other words, small differences can be greatly magnified by the state of the system. It doesn't forget the history. In fact, it magnifies the history. And it's sometimes analogized to this idea that a butterfly spreading its wings in Brazil could end up triggering a tornado in Texas. That small deviations in nonlinear systems can get magnified to lead to big changes. So here what we have is a depiction of 3 stalks. And this model came out of work by Edward Lorenz at MIT on atmospheric modeling. And these X, Y, and Z represent levels of the atmosphere or components of the atmosphere. And the equations are fairly simple, but they are nonlinear. If you go look at the underlying model here, what you will find, go, for example, look at dx here. This is a linear function, sigma times y minus x. You go look at dy. Here we have a nonlinear component. Where's the nonlinearity? Where's the nonlinearity here? Well, we have an x times a z, 2 components of state that are multiplied by each other. Here, we were just having the behavior dictated according to the difference between 2 states. Here, times some parameter. Here we have a depiction with this flow. This flow equals x times z. So the rate of this flow, ladies and gentlemen, or as it were, the multiplier by x is state dependent and depends on the value z. And similarly, if we go look at dz, you'll find it's x times y minus beta times z. So this is a nonlinear model. And you'll find it here depicted in state space. This, ladies and gentlemen, is x versus y space. This is x versus z space, and this is y versus z. You'll find these different lobes of the attractor. So maybe we'll run this in slow-mo. So I'm going to stop this. I'm going to slow it down. And I'm going to run it here. And you'll actually see it evolve. This is one lobe of it. It would appear. Now it's circling around another. And this is the trajectory being etched out. A trajectory that started here, evolved quite quickly through here, and now is circling around that point, but won't be there forever. What will happen after a certain amount of time is that it will come back and join this lobe here. And then it will go back and circle there for a while. So this is what's called a strange attractor. It exhibits several features that are of interest. One of them is that it's chaotic. The second is that it is of a dimensionality that is not an integer, but actually a so-called fractal dimension. Now, ladies and gentlemen, once again, I am showing here a depiction in the lower left, which we're going to come back to, which has to do with a lagged representation, where we're not plotting x versus y directly, but x versus a previous value of x. Okay? The final model I'd like to depict here, and we're going to be revisiting, so don't close these all together, is a model that is one we built in class, but slightly elaborated. And I think it gave you, okay, this one may be the one that gave you problems because its name is a mouthful. Hybrid Network Model, CMPD 394, Fall 2016, extended with degree histogram and emitting time series for both models. Okay, so I'm not sure if you'll be able to pronounce that, much less open it, but I'm going to give it a try, okay? So here we go. This is a model which we built in this very classroom not so long ago. And it's actually two models jointly. One is an SEIR model, and the second is a model of that same system, but at an agent-based level, okay? So we have an aggregate depiction of an infectious disease process, and we have an individual level depiction using agent-based modeling. Now, if we go run this model, as we did in class, what you will find is elements that are similar and elements that are different. I don't know if anyone remembers this model, but up here, towards the top, we have a depiction of state space. And what we'll find is that the state space of both models evolves towards a quasi-fixed point, to a point where it's almost in stasis. But the model that's stochastic in nature will continue to sort of cycle around this due to stochastics. The other model converges quickly to a stationary point, to a point where it's not changing, to an equilibrium in short. Okay, so here we had a depiction of those two models, and they exhibit some general similarities, but they have slightly different solutions for the stochastic and the deterministic model. So we had plotted out some things like the degree histogram and how it related, the number of times infected related to your degree, capturing the fact that people with higher number of connections were more likely to get infected. But a lot of our attention here is on the state space, okay? State space of these two models. We're going to be examining those state spaces in just a minute. Okay, so four models, three types of state space. I'd like to continue to cover our ideas here. So you may remember that when we depict state space, we can actually depict it in a very powerful way that exhibits what are called flow lines, okay? So we have something like this, and here's our state space with S and I, and we show these little arrows here, which indicate the direction of movement. So if you're here, the arrow indicates in what direction you'll be moving. How would we calculate that? So let's consider a system where we have differential equations for S. So ds dt equals something, di dt equals something. How would we determine in what angle this arrow points? I mentioned it briefly when I introduced this, but I want to see if anyone remembers or can figure it out again. Well, this is pointing in which direction state will be changing. How would we figure out from a given S and I how state would be changing? The rate at which state will be changing. How would we determine that?
Like run the simulation and measure it?
Well, we could do that, but in this case, the simulation didn't even go through that point. And yet we could determine that. So let me ask again. So we have ds dt equals some function of S and I. And we have di dt this is the rate of change of S, equals some other function of S and I. How would we figure out in what direction state is changing for this point in state space? Or that point? Yeah, I could do that. Thank you for raising that need, and I will zoom in here. Let me see if I can frob it to magnify it. Okay. Let's. Okay. I'm not sure that's that helpful, but trust me, these are arrows. Is that a good mix? Okay. So, ladies and gentlemen, how would we figure out what direction these arrows are pointing? You'll notice that up here they're kind of uniform, but down here they're pointing to the right. Here they're kind of pointing upwards. Why? How would we figure that out?
Is it F composed of G?
Sorry?
F composed of G.
Okay, it's a good idea, but basically you're onto the key idea here that, look, we could substitute in here the particular value of S and I that obtained here, and we will get the rate of change of S. That tells us how quickly we're changing in the S direction, right? We could plug the particular value we're at for I and S into this one. It will tell us how quickly I is changing, whether it's rising, whether it's going down. And the arrow just gives the direction of the movement of S and I. So basically, it's figuring, okay, you're going I, di dt equals 3 and ds dt equals -1. So then it would basically point somewhere like that. And so it creates an arrow here such that its direction is parallel to the values of this for the particular value of S and I at each point. So this tells us if you were put down at this point, where would you go next? You'd follow these flow lines. And you'll notice that if you follow them, let's take these here. Maybe we'll follow along here. Imagine we started here. We would follow this, and right now we're kind of going at a fairly steady pace up here until we get up into this region, and we'll bend around. You can see it flattens out here and it bends down here, and then there's kind of an eddy which will pull it round to this fixed point, kind of loops around here. So this is an example of state space and how we can use the values from these equations here to figure out the direction of these lines. And I'm not going to make you responsible for the exact, computing the arctangent associated with that, but the point is the direction of these lines is given by, it's made parallel to the values of this when considered as a vector. So basically it indicates how state is changing. If this arrow is pointing straight to the left, it means S is decreasing, I is 0, di dt is 0. So ds dt is negative, hence it's pointing left. S is decreasing, and di dt is 0. So it's not going up or down, so it's pointing straight to left. If only di dt was increasing, then it would be pointing straight up, right? I will be increasing, and ds dt equals 0, it's pointing straight up. If ds dt is greater than 0 and di dt is greater than 0, it's going to be pointing somewhere over in this direction. I is increasing and S is increasing at that point. So we just, in short, evaluate this by evaluating these things over here and using them to inform the direction of the angle. So this gives us a sense of where the system will go at any of these points. Do you get that idea? The general idea? Okay. So it gives us a kind of map for possible system behaviors. This is one particular trajectory. This is one particular run of the model that happened to start here, and it just follows the flows. It just follows these lines. In short, it just follows these equations over time. S is changing, I is changing, and as it's going, it's moving along, and it's reaching this fixed point where at that fixed point, what will these two be? at that place where it is stationary here, what will these two be? 0. Not going anywhere. It's not increasing s, it's not decreasing s, it's not increasing I, it's not decreasing I. Okay? So these are state space depictions, and it's quite useful to be able to depict this type of characterization when you can compute these things outright. Okay. So these are what might be called flow lines in state space. Okay. And they depict here. Okay. Now this is interesting because you're seeing a lot more of this than I am. There's some disjunction here between what you're seeing. You're actually seeing more than my screen. Okay. So the flow lines here can be calculated from those derivatives, and they give a sense of how things are changing. Okay. They give a sense of flow throughout the system. Okay. Great. Okay. Next, I'd like to talk about, and this is really a curious thing. I've never seen a situation where the monitor depicts more than my own screen, but we'll bear with this. Okay, I'd like to talk about fixed points. So fixed points in state space, places where it's not changing anymore, like this place here, correspond to place where the flow is stationary. All derivatives are 0. Okay, so here all derivatives are 0. It should say are 0, and these fall into several categories based on what's going on around them. Okay, and you can see one or two of those categories depicted in this. I'm going to switch over to this one here in the hopes that it will display more sensibly. Okay. Here we go, and no, it's okay. So here is an example of a point, and what you'll find if you study this is that there is a bit of a ring around this. Okay, so ring around that point, and what that indicates is that it's what's called a circular flow, but it's a sink. It actually sucks things in a circular way. In other cases, we may have what's called the limit cycle, which is actually where we simply get cycling around a certain point. And we saw that earlier with the predator-prey model. So if we go back to the first predator-prey model here, here we go. So it's the hares, lynx, predator-prey. What we're going to see here is a limit cycle. It's circling around a fixed point. It's not getting sucked into one that's completely fixed. Rather, it's cycling ad infinitum. The point right in the center here is actually totally fixed. This, if we had precisely, it looks to be 5,000 hares and 125 lengths, it would be completely fixed. We could test that here by stopping this. I'm just going to go, I stopped the model. I'm going to go run it for a very short period of time. That's this one here. And I am going to go click over, okay, I need to do model navigation. And I'm going to go down to the model. And I'm going to set this to be 5,000 hares. Oops, not 50. 5,000 hares and 125 links. Okay, 125. So if we run it out now, what we'll find is that it's completely stationary. It's not changing at all. There's a fixed point in the center. If I destabilize that even a bit, I make it 5,050 hares. Now we'll start to see a cycle around that fixed point again. Okay? It's cycling around. If I were to change that yet further, to change it, say, to 5,500 hares, we would see a yet larger cycle now around that same fixed point. So there's a fixed point at the center here, and it's a limit cycle around it that's cycling in. In other cases, that fixed point has a sort of sink in it which sucks things in from around it in a circular pattern or directly. Or it could be a source. Sometimes it can flow out. It's unstable. And if you're slightly off, you'll flow out. It's a fixed point at the center. It's completely imbalanced, but if you're slightly off, it'll flow out. It's what's called unstable. We can determine the flow around that point, around a fixed point, at a technical level for those who are familiar with it from your linear algebra class by computing eigenvectors and eigenvalues at that point. We compute at that point what are the eigenvalues and eigenvectors. It will tell us what sort of limit cycle it is. Now, when we're dealing with nonlinear models, an important feature is that we can have different equilibria in different regions of the space. So for example, we could have something like this, where on the one hand, we can have equilibria up in this area, and on the other cases, being slightly off, it can suck down to the bottom portion of this space. So on the one hand, we go to this basin, we go to this basin. On the other hand, we go to that basin of attraction, okay? So this is an example of different basins of attraction. It's like different areas where there's a lake at the bottom of each one. If you have a marble and you roll it down here, it'll roll down into this basin. If you have one here, it'll roll down into that one, okay? Recall that in a nonlinear model, we have state-dependent behavior. So the outcomes are path-dependent, and you can lead to multiple basins of attraction based on your past history. You're going to be going to this one or this other one. And where one starts is a key determinant for your future evolution, okay? Now, what I really want to spend some time on, though, in this lecture is the relationship between data from these systems, and it's not just from models, but from systems, and the underlying nature of the system. And I'd like to distinguish between the so-called nominal dimensionality of a space and intrinsic dimensionality. So let's consider this model over here, S, I, and R. So we noted here that if we wanted to pick the full state space here, we can depict S, I, and R coming out of the board. I would argue that that's a three-dimensional state space, 1, 2, 3. But the intrinsic dimensionality of that space is just 2 dimensions. That at any one time, if I run this model, it's going to be executing a trajectory on a plane within this state space. Why is that? Anyone argue that? Yes. Roman.
It's because the population is
Fixed.
Consistent.
That's
so
right.
for any state in our two-dimensional state space, we can reason about the full state of the system.
That's right. So S plus I plus R always equals some number. Right? 1,000, 2,000, 10,000, whatever it is. And as a result, if you give me S and I can just figure out R as that number minus S plus I, right? So here, R equals some number minus S plus I, right? And as a result, if I'm at a certain place here, and S and I, it tells me what R is. I'm never at a different R for that run of the model. And so, yes, I will be varying SI and R, but they will be varying in a way that really there's only, as we say, 2 degrees of freedom. There's only 2 things changing. Really, the third is just given by those 2. So, maybe we'll have, if S and I are very high, R is going to be very low, and if S and I are very low, R is going to be high. But there's a conservation here. There's going to be a plane in here, which is going to limit the freedom of this to really 2 dimensions. It's really, this model is only going to explore 2 dimensions of this 3-dimensional space. Why? Because given S and I, values for that, R has a fixed value. It's never going to change from that value. We know what R is here. So it's it's going to explore a plane of the state space, a sub-area of the state space, okay? And this is what I mean by intrinsic dimensionality. The nominal dimensionality of 3, but it's really only ever going to occupy 2 dimensions. So I'd like to take a look at several of these models that we've introduced and take a look at some aspects of their dimensionality here, okay? So ladies and gentlemen, for a given run of this model, of the predator-prey model, we have 2 dimensions that it's exploring, but it's really going around in a cycle that is intrinsically one-dimensional. It's basically just repeating this pattern. If I told you the time, you could actually tell me exactly what the values are of hares and lynx at that time. It just replays in a cyclic fashion, okay? Here we have a model that has a nominally 2-dimensional state space, but really at an intrinsic level, it's a single dimension. It's almost a line. It just happens to be embedded in 2 dimensions. I'd like to go now to another model. So I'd like to take a look at the this model that we opened last year. Actually, let's first go to the Lorenz Attractor. And the Lorenz Attractor, what we'll see is it's a 3-dimensional model. So we're going to run that again, okay? So I'm going to stop this one, and I will go run the Lorenz Attractor model. There we go. And what we'll see here is that this is a nominally 3-dimensional space. But you'll notice it's not occupying everything in these 3 dimensions. And I've depicted it here as 3 projections, the x and y, x and z, and y versus z. Can anyone visualize what are we seeing here? Based on what you're looking at here, do you have any sense of the structure of this in 3 dimensions? If you don't, that's fine. I'll show you what it looks like, okay? So just try to wrap your head around that, okay? What I'm going to do here is I'm going to load in all 3 of these data sets as output by the model. So I took these models and I output them, the data on the values as data sets, and I'm going to look at the Lorenz Attractor as a function of 3 dimensions, and I'm going to look at the trajectory that it etches out here, okay? And I'm going to show it here in a way that will explain more what's going on later. But we have something along this line's being shown here from a single depiction of it. You can see there's kind of 2 arms of it. It's intrinsically a 2-dimensional structure, but it's embedded in 3-dimensional space. You could see here, and these points, the points that are the same color mean that they were nearby in time. So you can see they're kind of skipping around. But as you rotate it around, you can see it's in 3-dimensional space. It's in a cube after all. But there's really a 2-dimensional structure here. So here we have a 3-dimensional structure embedded in a 2-dimensional space, much like this one we had over here, but it's non-planar. It's not just, we say it's a nonlinear surface. It bends around, okay? I will further look at some of these other state spaces, okay? So for example, we might look at the predator-prey aggregate space in this depiction. So here I'm going to do the predator-prey one. And we've seen that already on the graphs, but here we go. And I'm going to look at this in space. And you could see we have sort of a ring structure. We may depict it in a 3-dimensional space for reasons we'll see, but it's a two-dimensional ring structure that intrinsically is a single dimension. Okay, so ladies and gentlemen, within this context, we are dealing with these depictions of behavior within state space by directly plotting out the values of variables here, x versus y, x versus z, y versus z. And nominally, we may have one dimension in terms of accounting the stocks, but in terms of the intrinsic dimensionality, it may be simpler than that. There may be more structure there that limits it to a small subset of these spaces. And I argued for that model over there, that SIR model, where we have a fixed population. It's very similar. I'd like to now go on and talk a little bit more about what I just showed you, because I was actually engaged in a sleight of hand there. And I'd like to talk about these systems which are where we have multiple state variables, x, y, and z, for example, or SIT or SIRS, which are coupled together, or one depends on the other, okay? So remember that in a nonlinear system, how the system evolves over time depends on system state. Its behavior over time depends on this system state, okay? And often the evolution of each state variable depends on one or more other variables, okay? So let's go see where this is in our model here. I mean, we've seen it in several of these models, but let's make it very concrete. So I'm saying evolution of each state of a given state depends on several others. So let's go take a look. So let's go look first at the at this one, hares, lynx, predator, prey. So click on hares, lynx, predator, prey, and what we'll find here is that the number of lynx deaths depends on a hare density. Alternatively, we could look at the number of hare deaths here, and that depends on the number of lynx. So what I'm saying is the evolution of hares depends on lynx. Do you see that? Evolution of hares depends on lynx, and evolution of lynx depends on hare density, which is a function of the number of hares around, okay? Which depends on hares here. So in short, these two state variables are coupled. One, the evolution of one depends on the evolution of the others. Let's go look at that for the Lorenz Attractor. So we're going to go to the Lorenz Attractor, and we see that the evolution of y depends on x and z as well. How quickly y is changing depends not only on itself, its own value, but x and z. How quickly z is evolving depends on x and y as well as on itself. So what I'm arguing here is that in these systems, the evolution of one state variable is tangled with the evolution of the others. Okay? Here, the evolution of x, for example, in the Lorenz model depends on y and z. Now, the fact that they're entangled means they're coupled from an informational standpoint. If you have information about I over here, for example, it tells you something about S. If you have information about how R is changing over time, it tells you about what I has been and what S has been. It tells you something about them. They're entangled enough that the information in one actually tells you about information about the others, okay? And we can see this algebraically in a fairly straightforward way. So here, ladies and gentlemen, are some equations associated with the predator-prey model, okay? So these equations were captured in that predator-prey model, the aggregate model that we've been running, the one that leads to those cycles, very nice cycles. And you'll notice that here, I'm saying the rate of change of x equals some function of x and y. It's just the type of thing I've written over here on this board. And similarly, the rate of change of y equals some function of x and y. But from a standpoint of prediction or characterization, I can actually solve these things such that I could say, okay, how does y of t relate to the values of x? If I know x and I know the derivative of x, if I see how quickly it's changing, I can basically reconstruct y. Given just this information about x and x dot and the values of alpha and beta, I could tell you what y is. They're coupled, and therefore you can reconstruct one from the other. There's enough information in x about observations of x that I can reconstruct what y is. There's enough information in y that I can reconstruct x as a function of time from observations only of y. Now that's significant. What it means is they're so tangled that by observing one, I can get information about all of them. Okay? By observing x, I can get information about y. By observing y, I could alternatively get information about x. By observing the lynxes, I could know what the population of hares has been. By observing hares alone, I could know what lynx must be for this model. Okay? Now, this was reflected formally in the 1980s, the early 1980s, based on some observations that seemed to suggest that it really had some practical utility. There was a very nice theorem proven where essentially you could say that for a nonlinear, a complex system with some constraints, you could actually reconstruct the full state of the system. Information about the full state of that system, all the state variables, from just an observation from a single time series from that system, from one variable. If you can measure one thing out of this system over time, with some qualifications and provisos, you can reconstruct the internal state of the entire system. They're entangled enough that just seeing one thing tells you about the whole thing. It's almost holographic. From one component, you can reconstruct the whole thing. And this is Taken's famous embedding theorem. And it's a very practical methodology. And we're going to see how it can be applied. Okay, so if we observe y is just one element of the system. Maybe it's the value of a stalk. Maybe it's the value of a flow. We observe y, and we observe it over time. It turns out we can reconstruct the system. And the key elements of this from the embedding theorem, which were demonstrated at an empirical level by Doyle, Farmer, and others in the Santa Cruz Collective, was that basically you can create from observations vectors. So synthetic vectors consisting of one observation, an observation a certain amount of time before that, twice that amount of time before that, and so on. And this is a vector. So all we have is observations y of t, and we're going to construct a set of sort of synthetic observations consisting of vectors. Maybe they're vectors consisting of three components in linear algebra. So y of t minus 1, y of t minus 2. Maybe another vector would be y of t plus 1, y of t, and y of t minus 1. Another vector would be y of t plus 2, y of t plus 1, and y of t. We're going to create those, okay? And then we are going to populate our space with these vectors, and we're going to see what it looks like. So in order to get a sense of this, ladies and gentlemen, I'd like to go back to our models here and go back and take a look at those models, at some of those graphs we've been pretty much ignoring. So here, I'd like to start with the hares lynx predator-prey model. So we're going to start with this, and you'll notice that within each of these models, I have depicted the state space, and then for most, I've depicted this alternative space, which I kind of waved my hands at. So here's hares versus lynx. Here we are. We're running it out, And here's hairs versus a delayed version of hairs. Ladies and gentlemen, this was motivated precisely because of this basic idea here that we create vectors consisting of the value now and the value one time ago, for example. Okay? So this is a depiction of just using hairs, not considering links at all, just hairs versus hairs one time ago. We see something that is reminiscent of this. This is actually the same structure as this. It's just stretched. It's just distorted. Here's links versus links at time t minus 1. And this is also going around in a cycle. Why? Because links incorporate the information about hairs. And basically what Taken's theorem says is that if you construct a space out of these sort of data points, like plotting hairs versus hairs minus 1, hairs minus 2, it will basically be the same as the original state space, just with some distortion. So if the original state space is a kind of ring with a hollow point in the center, the same will be true here. If the original state space was 2 dimensions, embedded in 3, now you'll see a 2-dimensional structure coming out of this. So this is our hairs and links model. Let's go look at some more, okay? Let's go look at this Lorenz Attractor model. Okay, the Lorenz Attractor is this chaotic system. And here we have x versus y. We'll have a kind of a shape that is 2-lobed. This is kind of wings of the butterfly. And ladies and gentlemen, here, down here, we'll see x versus previous x of t minus compared to x of t minus 1. You may recognize the general structure. These 2 lobes correspond to these 2 lobes. It preserves the basic structure of it, even though it's squished in some ways. It's basically allowing us to understand the structure of the state space. And when I showed you, when I mentioned my sleight of hand earlier, when I showed you those plots here, what I was actually plotting out for the Lorenz Attractor, this was just plotting out points in 3-dimensional space of the form x of t minus 1, x of t minus 2 for different values of t. And that allowed me to sort of reconstruct what the underlying state space of the whole system is. We're going to try this for a few more here. Predator-prey agent-based. This was, again, reconstructed from the number of hairs at time t, t minus 1, and t minus 2. This is a time series. Let's be clear about that. What I'm plotting out here is from a time series. This is the number of hairs over time. There's the number of hairs over time. And all I'm plotting out here is in 3 space, a given point, the next point before it, and the next point before it. And it gives me a reconstruction of the actual state space of the system, the space of hairs versus links, even though it's only from hairs data, because the 2 are so tangled together that looking at the data from hairs tells me all about links. Hence, it's captured this same basic structure that we saw here, and I'll go back to it, that we saw here with hairs and links. So with the hairs and links, we saw the structure of the space basically consisting of this ring, right? Hairs and links. And that information is precisely encoded in when looking at hairs alone or links alone. Let's take a look at some more of these. So here we go. This is hairs versus links, but we can get the same information out of hairs alone or links alone. Just look at those time series, but in this delayed observation sort of way. Okay, let's go to this one. Here's our hybrid model where we have SEIRS and recoveries here. And I'd like to look at its output, okay? So if we go and rerun this, you may remember what we see here is a depiction of each of those states in space, and it comes down to a situation where it reaches an equilibrium pretty quickly for the, it goes up, comes down, and reaches an equilibrium. Very similar to the models where I showed the flow lines depicted. Meanwhile, this is the stochastic system. Let's go see what those look like in space, according to the so-called delayed embedding, where we're looking at it versus it some amount of time earlier. Okay, so we're going to go here and look at this one here. SEIRS, and oh, I gotta pick a particular one. So this will be which one? It'll be the prevalence from the ABM. Okay, the number of people infected. Actually, let's do the prevalence from the system dynamics one first. Okay, the system dynamics prevalence. Here's system dynamics prevalence. Okay, in three-dimensional space. So what you see here is basically a two-dimensional structure, and it sort of moves along here, and it loops back, and so on. And I can stretch this in some ways. I can view it with a longer delay, for example, between these. And you'll see it's not quite two-dimensional, actually. But locally, it's sort of one long trajectory. So we started here, and it came down, and it reached a fixed point. I'd like to look now at the ABM one. What does the ABM one have different? It's stochastics. So here's an example of the ABM one, for example. So that one isn't quite as neat, but you'll see in three-dimensional space, it's fairly compact. It exhibits these trajectories around it that reflect the fact that there's this sort of cycles associated with it. And you can see that even though the system itself is nominally four-dimensional, it has SEIR, the actual depiction here is basically three-dimensional, and it's even somewhat thin on its third dimension. Okay, so here, ladies and gentlemen, is a reconstruction of the state space of this ABM using just one time series, just a single time series. We can do this reconstruction of the underlying system. So you may ask, well, that's interesting, and it's certainly pretty at times, but what's the good of this? You know, to what ends can we put this? To what degree is it useful? Well, it turns out it's very useful. It's useful in a couple of regards. Okay, one thing is, given observations, we can recognize hidden structure behind them. It turns out that if you go look at the Lorenz series, so maybe we'll go take a look at the Lorenz series over time. So I'm going to pull up the Lorenz model, and we are going to run it, and I'm going to look at the value of a given stock here. So the Lorenz model has three stocks, X, Y, Z, and I'm going to run it, and I'm going to look at the value of one stock. I'll pick X without particular reason. So here we have a depiction of X over time. The order behind this is not particularly clear. You could be excused for thinking it looks quite random. If we were to plot it out on a plot here, I'll go over to Lorenz here and go and call this up, and I will go create from the palette. I'll go create a time plot here, and I'll make it a time plot which will go for 1,000. It'll go for 1,000 latest samples, and this will be state variable plot. Okay, and I'm going to plot out the value of X. Okay, here we go. It'll update every one time unit, and here we'll run this out now. Okay, we're going to run it out, and we'll see as it plays out. And as I said, you could be excused for thinking that it looks almost random. It looks quite unordered, but really there's a lot of order behind it. The order behind it lays in the underlying structure of the state space. The fact that you have these multiple lobes and they're circling around of them. But that hidden order behind what looks to be random isn't obvious without this state space reconstruction, without this ability to kind of look at these time series and discover the hidden patterns behind them. So that's one thing. And just in this past month, we've had one of the graduate students from our group display a time series, for example, which looked by purposes, much of it fairly random, and a lot of structure stood out of that, a lot of the hidden structure that gave rise to it. Secondly, you can assess the dimensionality. So what is the intrinsic dimension of this curve? Will give you a lot of hints as to how complicated a model has to be to explain it. If it can be explained in a simple planar structure based on the observations, it might point you to a model which has fewer state variables, fewer moving parts, a simpler model. If it has high dimensionality, it might point you to a model that needs more moving pieces to explain it. So it can give you hints as to how much model structure you need to capture. It can also give you a sense of sort of what can lead to what. The fact that you never get, for example, you never reach a certain point within the system may be quite obvious from the time series, and the general structure may be evident. By formally estimating the dimensionality here, we can go through a process whereby we can get some sense of the model complexity that is needed for it, and there's some techniques called correlation dimension that allows us to do this. And then finally, and very excitingly, just recently, there's been a series of papers that have appeared on a technique known as convergent cross-mapping. And this technique basically uses these sort of reconstructions from time series, the sort of reconstructions we're doing here, or that I am showing on these graphs. It actually uses that to figure out what is influencing what within the system. Which thing is influencing which other thing. That's not a trivial thing if they're interacting jointly. So if we can reconstruct this sort of depiction, and I'll put it up here with the Lorenz, or if we, for example, have data from about this sort of model, or we have data on a model that from a real time series from the empirical world that shows us several factors. Basically what you can do is reconstruct this same depiction for multiple variables, for multiple time series. Maybe you have one time series for different types of animal species. And you can, by analyzing these, reliably arrive at understanding about which one is influencing the others and how much so, directly. Using purely those time series, you can tell to what degree are they just correlated because something else is driving them both, like weather, and to what degree are they correlated because one is affecting the others, like predator-prey, okay? So with predator-prey types of situations, it may not be obvious which of these is influencing the other. Are the hares influencing the lynxes or vice versa? But it's precisely because we can use these state space methods together with what's called convergent cross-mapping that we can assess this. Now, when you do this with real data, the results are sometimes messy. There needs to be some exploration. You look at it for one type of delay, the structure may not be entirely obvious, and you really need to experiment with different delays. For example, go to a delay of a larger delay here. I'm going to do 20, and here we can elicit some additional understanding of structure that helps us understand some of the ways in which the system evolves. So again, points which are similarly colored are associated with similar times. So here you can see it spending more time here. Later it becomes more mixed. This is one trajectory out there. And then modifying it yet further, here we can get a depiction of multiple trajectories. Now you can sort of distinguish multiple particular swings through this system. So convergent cross-mapping provides us a way, and I'm not going to explain the details of it, but taking several of these graphs from different time series and rigorously showing which is affecting the other using just those data. Without actually being able to yet fully reconstruct the system, it lets us reliably understand, that this is influencing that, but not vice versa. Okay? So state space reconstruction is an important element of complex systems. It's an element that isn't totally clear, but suffice it to say that when we have these nonlinear systems, these systems that are coupled, because any one piece of that can tell you a lot about the other pieces, we can use time series data about those systems in very powerful ways, in ways that give us hints as to what a model needs to look like to explain the system, like how complicated it has to be, and hints as to what's driving what in the system in ways that will give us clues as to what the equations need to be to capture that, or what the components of the agent-based model need to be to capture the influences. In short, we're dealing with a situation where there's often hidden order in the system that isn't obvious from the time series, but which can be elicited through these techniques, like this so-called embedding, where we place it in a space from lagged version of a time series, looking at the time from just that one time series, successive vectors from itself now, a bit earlier yet, we can actually get a lot of understanding of the hidden order that lies behind it. So this is one of the ways which, using empirical data, using modern techniques, we can get some understanding of how the system that gave rise to that data needs to be structured. In other words, gives us hints as to how to model that system most effectively, using just observations from the world. So observations from the world, you might think just by one type of observation, we fall far short of what we need to model the system. In fact, often for these sort of systems, one type of observation repeated many times can give a huge amount of understanding about the underlying system. Okay? So that's my lecture for today. On Thursday, we're going to be talking about a different type of reasoning that doesn't even require empirical data, but can tell us a huge amount about how we need to build relationships in the model. And that type of data is dimensional data. Data not about intrinsic dimensionality, but about the physical dimensions involved in the model. And critically, it can also help us quickly recognize cases where a model has errors in it. Errors that could easily trip us up, but which can be found very straightforwardly by reasoning about the dimensional structure of the problem. So that will be Thursday, and then we'll wrap that up. Now, also due Thursday is a problem set, an assignment. And I'll be holding office hours today and on Thursday, and I'm glad to discuss that. I will also tell you, because I know you folks are probably starting to plan your final exam schedules, I am planning to hold one, or if needed, 2 review sessions for this course. Those review sessions are typically 2 hours each, and I will lead you through a set of discussions of what I consider the most important material. I will also be giving some example questions for you that you could explore as possible questions that might be on an exam. Okay? That will be coming up. between Thursday and the final exam later in December. So that's all for today. I'm glad to meet any of you for office hours, and thank you for your attention. Hi.
When is the deadline for the motion?
Okay, great questions. Thank you for raising that. So what I'm asking for undergraduates is project turn-in, if at all possible, by Thursday. Now, if that is simply